record, start the recording. And yes, Venkatesh, can you reshare?
Yes, sir. But the share is not
Oh yeah, share is not
finished.
enabled.
Not sharing, sir.
Yeah.
Yes, sir.
Just can you try now, please?
Yes, sir.
Yes, Venkatesh,
Solid 3.
I was telling this device dimension which you have taken, this curvature. Okay. This curvature, can you go to this component solid 3, not copy solid 3, 3 only. Select it. No, don't double click. Only one time. Select. Select the box, no? Nearby box. Yeah.
Yes, sir.
Next go. Select solid 3. No, is you have selected copy. Go to solid 3 upside. Yes. This
Yes,
one.
sir.
Select it. Yes. Now, can you go to solid 2? Here. Solid
Yes, sir.
3 should be the band, no? Why it is not showing band? Okay.
Sir, it was banned, sir.
Unshare your screen, please.
Officer.
Now you can see that, let me open a project in CST. Let me open C section, which I explained you, right? Let me open your project. Can everyone see the screen clearly?
Yes, sir.
Okay. So here you can see in my screen, if I take the dimension here, okay, let me change the dimension according to, you know already. So let me know the dimension. Let me edit those components here and how it changes, right? Solid 1, can you tell me what is the solid 1 dimension? Tell me please, how much is there? D by 2. D by 2, what was the value of L?
L 42.8, sir.
42.8. Okay, let me change this in the schematic. It is translate, no issues. Okay, no problem. Let me design. I think editing in the same is getting difficult. Let me start a new project. What was the frequency? 2.4 gigahertz, right?
Yes, sir.
So let me define the antenna. I'm quickly making that. Doesn't matter, no problem if something is we are able to end it up today, because actually I wanted to do loop antenna, but that we will do it later on. So let me design this here, 2.4 gigahertz. Okay. Frequency, you took it from 0 to, let's say 3 gigahertz. Let's take 6 gigahertz. Okay, E field monitors, I am keeping it in Far field not required. Okay. 3. Let me also take at a 3, 4. Oh, main will be 2.4. So 2.4 gigahertz is my monitor, and 4 gigahertz, and this is, we can actually check, particularly we want to check for 2.4 gigahertz. That's why. Next we went, let me save this project with the same name. It is 2.4 gigahertz. 2.4 gigahertz folded dipole, section C. Okay, let me finish this. Let me start the project now. Okay, this is initializing. Let me create again quickly the project. Perspective plane or cubic structure. Let me model. Let me introduce a cylinder. Cylinder dimension. Can you tell me length of dimension? Z-axis. We're creating. Please tell me dimension. What you said? Outer radius. Radius is for 2.4 gigahertz. How much is the radius? Radius of rod diameter. Diameter divided by 2.
0.2, sir.
Okay. We want to create it outer radius d by 2. X center. This is okay. This is Z. Okay. Z. You said L by 2. What is the length? What is the length?
42.8.
2 magnetic material preview. D you said, sorry, please tell me again. Diameter
0.4, sir.
0.4 diameter. Diameter is 0.4, right? For your
Yes, sir.
case. Okay. And this is diameter. Okay. And then length is how much?
42.8, sir.
42.8. Okay. I've given this L by 2. We got a cylinder also. No problem. Now we want to copy this. So let me take this component. Okay, done. Then the component achieved. Let me add. I'm not changing today color or anything. Let me consider this same. Let me go transform, copy, and copy where we want to in the X direction. Now S distance away, isn't it? S or S by 2? S. So we want to copy this and paste it. Let me say preview. It will ask S how much? 10. Let me give. How much is coming spacing now?
6.8, sir.
Why? Say 3.4 into 2, right?
This radius is 3.
Yeah,
Yes, sir.
6.8 you took radius. Okay, fine. We created 2. Okay, apply. Okay. Okay, done. Next is we are taking the gap cylinder. So, okay. Gap cylinder is take another cylinder. Orientation is same. Orientation I am keeping it as how much in Z direction. Or is the diameter coming? 0.4 you said, right? So
Yes, sir.
D by 2 is the diameter. And here we want X center. Z minimum is G by 2. What is the gap coming?
1.1, sir.
Minus G by 2 to G by 2. Okay, let me do this. It's a vacuum so that we can remove this part. Preview. G value how much? Sorry, tell me please.
1.1, sir.
1.1 millimeter is the G value coming for this. You have written 2400 megahertz, right? Yeah.
Sir, it is gigahertz and megahertz, sir.
No, there you have written cut away highlighted portion. Okay, now dipole created. Now what we have to do next is we have to create a cylinder again. So we are taking the 4th component, cylinder solid 2. What is the dimension? Outer radius is, you said, D by 2. And X center, this time we want to orient it to the X. So we will make it like this. and let we keep it as for in x dimension as minus at s by 2, right? Yes, and s by 2 we want to keep oriented s by 2, x minimum s by 2 plus of s x direction, no? So it will be minus of minimum will be minus of 0.2, any value we can take, so it doesn't matter. And this is
Sir, jet center.
just a minute, I'll change it, that we will put it plus of 0.2, and here z center we want to keep L by 2 plus of R. Yes,
Plus R, sir. Yes, sir.
L by 2 plus of R. Let me write as a L by 2 plus of R. It will ask me what is R. I will enter there. Preview. What is R?
3.4, sir.
3.4. Okay. Now let me see it is coming correct. Very nice. And let me do it. Okay. Fine. So we are ready with this thing now. Now we have to do this component is added. Oh, sorry. I think this component material I need to change. I put it vacuum. It was vacuum. Let me check it to PC. Okay. Done. Now we want to select the faces. So go to pick face. I selected one face. And secondly, let me go here. Let me rotate this. It's also visible. Pick face. Double click. Okay, done. Now we have to go for lofting. So let's take cancel. What is this rotation now? Loft. I have to loft between two surface is fine. And if we keep it here, because with the same radius it should come. So if we loft it, oh. Now if I loft it and if I change it, let me see preview in between them. Yes. So you took it as how much you took this smoothness?
Sir, 3.4, sir.
3.4. It will not come the value of 3.4. Now that's what I'm surprised.
Okay, sir. I will check. Sir, it is the radius, right, sir?
Well, yeah, radius. Yeah, radius is 3.4, correct. But I mean to say the value here, smoothness cannot be. This is the only purpose why I am doing it now in front of you. Because you see, what we create here in your structure, it is coming as like some closer. So have you selected properly R? If it is R, okay, from here lofting is not from the center. If we see, increase it, preview, it is going like this, right? I don't want this corner. Actually, we want a proper lofting. So our value is 300, no? 0.3, 0.2, it is only coming value. The radius is coming
Sir,
0.2.
in the last experiment, you take the radius, sir.
Yeah, I took a radius of wire. You remember that time we didn't consider the radius. Are you able to follow me?
Sir?
Last experiment what we discussed. Okay, folded dipole. Online calculator for this.
Sir, as it will be a semicircle, the radius will be 3 points, sir.
See, this is our calculator, no? So you can see here we didn't consider that time radius in the last experiment. Now my question is, if you are using this radius, okay, here, okay, how much should be the value? this particular portion, I mean, if you are taking that curvature here, right? This curvature. Last time we didn't consider, we took it simply lofting by 0.2 because 0.2 is the radius of wire. I mean to say this radius, we need to loft it with the same angle, na? Then only it will come good curvature. And similarly, this one also. So what you have chosen, that is going to matter. Anyways, let me go here and let me choose this lofting of this one, 3. This one. If we go for 0.1, if we say minimum twist, okay, you can choose for minimum twist. This will be best. You can choose for minimum twist and then perform this. Next, you know already, right?
Okay.
Okay. Again, I need to change because unknowingly I put the material component as vacuum, which is not vacuum, PEC. Okay. Other things, you know, it's fine. So I'm ending up this project now. It's fine. Thank you, everyone. Shall we go for the next? Everybody could understand this. Design, show the results for 2.4 gigahertz, a folded dipole with the dimensions given. Can I proceed for today's experiment now? I'll quickly take 15 minutes only to complete this practical, and then after I will give you time that you have to create a loop antenna. And for that, let me restart my project. See, actually for this, before that, I want to make you understand. In theory, we have discussed about the loop antenna, right? Loop antennas are what? They are a closed path of wire, right? So they are also the type of wire antenna. In the loop antenna, what we are going to do is there is going to be one loop of the wire and one is going to be the feed point out of this for connection. So there is a wire from which we can say port 1, port 2 will be connected, and this, it is following a radius. The another loop which will be there, which will be existing outside this, like this, okay? And this particular loop antenna, to design it, how it is in the shape. So let's create a loop here in the CST. Now, one important thing is a wire antenna. If we say this is the loop antenna with number of turns, okay, it needs some base, because if you remember, loop antennas are placed in a vertical plane, okay, or whatever plane is there, the loop which is not connected, that should have some support or base on which it can be drafted. So that's why they are generally made in a plan, or we can say a planar or patch type of antenna are there. In case suppose you make a wire type of loop antenna, which is only used for one or two purpose, loop antennas having very low efficiency, but they are very good and adequate enough in, sorry, they have good efficiency, but the thing is the gain is very, very less. It is not of much value, but they are very good in application for the direction finding. So what we can design is, we can design a planar antenna this time in place of wire antenna. So keep in mind, this will be a planar antenna because we need to pack the structure into on a base. So let me select a frequency. For example, I'm similar to the last time, I'm taking just a random value first, and then after I'll give you the design equation values for this, which you have to define. Let me keep all the field monitors, power flow, everything open. For 3 and 6 gigahertz, we are going to check it. We can name the project as a planar loop antenna. Finish the project. You are on the same page. Here after coming, you can, what you can see, you can change the plane WCS first, and you can find you can go to the perspective plane to front plane so that you can see the front side of the screen. Okay, to design this thing, because in loop antenna what we are going to do is, if you see the axis here, okay, we have x direction here, y direction upside, and obviously z direction in the front. So we are in the xy plane now, so we have to design in between them. So we are putting in xy plane a ring, or we can say a loop. So select from modeling, select a ring. Now ring is what? Ring is a solid ring. So obviously solid ring is in circle shape. It must have a radius, inner radius, and outside radius. So I'm taking for Z orientation one ring we are making with radius, large radius is given as, for example, 17, 15. We are making the loop of 15 mm. I'll give you the dimension values later, but currently just understand this thing. And suppose the thickness of ring is 2 mm. So we can say 13 mm is the inner radius and it's going up to 15 mm. Any problem? Same material,
No,
X
sir.
orientation, Y this. So we'll preview and we'll do okay. So you can see in preview one ring appeared. You have to select for ring torus. Component is here, torus component. Preview, okay. Once you get it, or component has arrived, so we can see here there is a structure available with us. Now what we want is, from center to this, it is coming. Radius is we took as 13 centimeter. And from center to the outer side radius, it is coming as 15 centimeter, 15 millimeter, sorry, everything is in millimeter. So here from center, we say it is the direction of Y. Can you see the plane here in the right side? Plane here is in Y scale is here and X scale is here. So actually what we do is we have to create a structure which is from here to here, and we want to create a feed point. So to create a feed point, go select a brick. There is a brick option, first one, first component. And in the brick you go and let me write it as a brick. And this brick I'm having, for example, it's in X direction, Y direction, and Z direction. We are going to check it. Go to the perspective plane. So you can say, okay, let's first say, see this properly, what we have designed. If we go in the same plane, can you see this ring now? If it is a ground level, can you see how it is shown in the plane, right? Could you understand the loop? Hello? You exactly put in front of your line of sight. You can understand this is the thickness of 2 mm which we took, and there is a ring lying over the surface. Is it looking like? Is it exact orientation? Okay. Now what we are going to do is again go to the normal plane, perspective plane only. And now we are going to design a brick. So let's take a brick. Our purpose of brick is what? To create a gap here. What is the gap we chosen in the dipole? Anybody remember? What was the gap in the dipole? Last practical folded dipole also, what was the gap?
1.1, sir.
What are you telling, man? Okay, for your practical, 2.4 gigahertz, right? What in the basic fundamental we took is a 2 mm, no? So let's say,
Sir.
yeah, 2 mm. So let's say we want to create a gap here of 2 mm. Our purpose is to create a gap here of 2 mm. So how we can do is, we can take knife, we can cut it, isn't it? To cut it, what we do, first we make a component here in a shape of brick. Brick is a cuboid shape structure, or we can say as same PEC material bar, we are going to place it here. And we'll take the length of the bar a bit more. So if we say from center, it is center to outer radius is 15, isn't it? Currently this ring we having outer radius up to here at the end is total 15 mm. So what we are going to do, we are going to take the bar radius little bit more, bar length little bit more than that. So what I can do is I can decide a bar which is starting from this. Now you can see in the solid or in a cuboid structure what it is showing. If the bar is going to be placed like this, what is there in the x direction? X direction is this thickness. Okay. What is there in the y direction? Y direction is our length. So we can say plus of y going here, it is minus of y. So from 0, and if I go down here, it is coming up to minus 16 and minus 15. Then if I go some more, so let me take it as a minus 16. 0 to minus 16. What I took is, I took the length just more than that, and I am going to insert a component here. Okay. Here, and what is z is? In z direction, what is there? Z direction doesn't matter if we take 1 or 1. Okay. This is our z direction. So we can say we can take it as total 3 mm. Okay, no problem. If we even take this 3 mm, it means from center 1.5, 1.5, or if we take 336 mm. Because what is the rod diameter? What is the ring diameter?
2
We
mm.
took, yeah, we took d by 2 is a 0.4, no? D is equal to 0.4. So we want anything in this direction also. This can be more than that. So we can also, you can choose to decide a small road like this, or you can decide a random value. It doesn't matter because we are just going to use it for cutting. Like this if you make, or like this if you make. So let me take the values now. Somebody unmuted, please mute yourself. Munishwaran sir. Okay. So here what you can see is that if we have this structure, for this to design it, we are taking a brick, escape, and the brick dimension. You see what it is asking? What is x minimum of brick? Our purpose is to make a rod there in between this. Okay. So I'm writing it as x minimum as -1 to 1. Y minimum, y is the direction you can see here. I am writing it is here as from x minimum is this is the orientation, sorry. See, this is x orientation. Na? So in x orientation, we can say x direction, mine, yeah, is correct only. And why I want this to be starting from 0.
So y minimum,
yeah,
minus 16.
Minus 16, and y maximum can be 0. Okay. And in z direction, I want any value I can take. Let me take 2 minus of 2, because it is just a additional area more than the diameter. So in z direction only, the thickness of this is there. So if I take anything more than 1, because actually we took the radius of this point 2 only, so we can take any value, doesn't matter. So let me write -2 to +2. With this, what happens? You can see, let me remove the mess which I created in the screen. Is it clearly visible to everyone? Is it clearly visible with this? Can you see this, what we did? We created a rod, okay, of any direction. Doesn't matter if I take z more or less, but only thing is the direction of z should be more than the thickness of this rod. That is the only purpose. Here it can be 16, 17, a longer rod, doesn't matter, but should start from the any point. We just want to create one portion. You will understand this now. Let me do this. Okay. So you can see with the same PEC material now, one more component has been connected like this. Could you understand? Could you understand, everyone?
Yes, sir.
Now with this, what is our purpose is, we don't want to make it a stylish. Reason being, the bar is not going to be used as a loop. We are just using the bar to cut the portion. So now what we are going to do is select the component. So I selected a component. What is this? This is bar, this is solid. So select the rod first, solid one. So we have selected the solid, and from this ring we are going to subtract the brick. Then we are going to have a gap. Are you following the idea? So I took the solid one. This is the bar. So from this bar, solid one ring, if I'm going to remove this bar, then I will have 2 points for connecting feed, which is of gap. How much? How much is the bar? It means how much is the this x dimension we have taken, and x dimension we have taken -1 to +1, right? That is 2. -1 to +1, how much is distance? 2, no? -1 plus of -1. Yes. So with
Yes, sir.
this, let me select now. I selected a first component, ring. Select ring. Go to Boolean. Here go to subtract. And it is asking on the screen, select object to subtract from component solid one. So selected the component already, and now we have to select the component which we want to subtract from. Okay. So I selected now solid 2. So I want this bar to be subtract from solid 1. I done it. It is showing now on my screen. Subtract component 1 solid 2. Component 1 solid 2. It means you can remove this component part. You can say subtract solid 2 from solid 1. And that's what we want to do. If want to confirm, if I press enter, you can see that portion has been removed and we got a gap. Could you understand? Because that was a PEC material only, na? Same material. So it was easy to remove that structure out of this. Could you understand the fundamental? Yes, no?
Yes, sir.
Now we are going to do is what? We are going to make another loop around the same this. So select a torus, same dimension, same orientation we are going to take. Orientation is Z and larger radius, because previous one was 15. This time let me take 20, because we are taking a value. Small radius will be again 2, because the thickness of the wire is same. So we are going to take 18, 20, 18. 20 is the outer diameter, inner diameter is the 18. X orientation, everything's okay. Preview. It is showing another one. Okay. Third one, let me also make another one. Let me take this is 23 and 2 meters, same diameter outer than this. 21, same value. Preview. Okay. Third also came. So we got actually a loop structure of 3 loops, isn't it? And now let's simulate. So to simulate this, we have to give the first feed point. So similar to dipole, we are going to select the phase. Here we have to select the phase. So go to simulation, pick center, or you can go here, pick points, which is pick circle center. So I've selected for 1, and similarly after rotation, I'm going to select it for 2, Both the values are there. You can see on the screen it is showing P1 and P2. P1 and P2, two ports are created. Okay. After that, what we are going to do? Go to discrete port. Select discrete port. Nothing to change. Same thing will remain for simulation. It will be 50 ohm. Nothing we are going to change. Fine. And then here you can write 30 dB. That also is your choice. You can do it for 40 dB also, no problem. Apply, start. Okay. So this is our experiment number 5 for loop antenna. Let it run the project. Everyone make this project now of a loop antenna. We'll check the radiation patterns out of this. Loop antenna is a magnetic dipole, right? You'll find in the direction of maximum radiation, it will be opposite from the pole, what we have seen in the dipole before. Yes, with 3 warnings, project successfully ran. Now we are going to check. We are going to check the result. 1D results available, or more importantly, go to far field result. So at 3 and 6 gigahertz, you can see the apple shape it changed here. Is it different? Are the radiations different from the dipole which we have done? Here in the 1D plot, you can also see the Cartesian gain plot here, or a far field pattern that you can receive, or you can also see this in the polar plot. At 6 gigahertz, you see how abruptly it is changing. You can see the pattern which was there for higher frequency which you are observing. At 3 gigahertz, because it's nearby to the design equations only. So we can say uniformly divided two fields are available. At far field pattern, it's changed. Similarly, in 2D, if you go to this 2D, in 2D E field, if you see in the loop antenna, animate it, you can see the 2D field which is observable here. Now, interesting thing is the loop 2 and 3, solid 2 and 3 which we created, they are not having electrical connection, but radiation persists. If you want to check the surface current density of anything, this is why we can say the principle of electromagnetic transfer you can realize here. The surface, these are surface current density. Can you see this? The feed point is only to 1. Can you observe it? At 3 and 6. More number of, rather than taking more number of frequency, please take more number of observation, record it appropriately for the loop antenna, which can give you more values, understanding of the part. Is the power flow at 3 gigahertz. Let's see VSWR, because at 2 gigahertz, below 2 gigahertz, you can see it's a mismatch, but for 2.4 gigahertz, it's 2 gigahertz onwards, it is having lower values, or we can say no values of the VSWR available for this range. Let's see 2D, 3D results. How's the H field? Everyone, please make this structure and let me know.
Can I share, sir?
Yes, please. What's your good name?
Venkatesh.
Okay, Venkatesh.
Sir, I have a doubt, sir.
Yes, please ask.
Sir, can you please show me that picking the circle centers?
Sorry, picking the circles in a sense?
Center, the pixel. You did the pix thing, na, sir?
Here, what
Sir,
I
adding
picked.
port, sir.
Okay, in the port. Okay. Actually, here in the component, let me go to 3D. Go to component again. Solid 1. And we are going to add any component here. So let's our component be selected. Suppose this side is, or it doesn't matter which orientation we are. So when this was select perspective view, and in the perspective view, you can first select the one of the area. Our idea is to select this face. So you have to go to simulation, not in modeling. You might be doing in the modeling. Go to simulation, and there is a pick point option. Go to pick circle, center won't come, pick point on the circle. And if you select first and then double click on that, can you try this? Share your screen. Share your screen.
Yes, sir.
Yeah. Yeah. Now select, go to pick points. Yes. Select center. Yeah, is one on circle. Yes. Now double click, grab it over this. You are doing it a simulation, no? Have you selected the component? I think previous step already taken. That's why it is not picking again. Go to again, pick points. Any point, just no, don't go to arrow. Don't go to arrow. Only select pick points. Yes. Now go. Double click. Double click. Yes.
Yes, sir.
Rotate it another side. Done. Yes. Discrete port, run. That's it. Yes. Who was ready to show? You can unshare, please.
Okay, sir.
Yes, sir.
Thank you, sir.
Permission.
Okay. What's a good name?
Venkatesh.
Venkatesh, just give me a moment. I think after 5 minutes, I'll 5 minutes is rest time, and then after we'll check the screens. Any problem is there, and then I will get back to you. Give me 5 minutes, please. 2:55. I'll stay connected, everyone. At 2:55, we'll see this thing. Okay. Yes, students, before you share the screen, I think as nobody has problem, let me see, because we have done the same dimension design, everyone, right? I trust on you. So I'm not checking this now. Am I audible? Am I audible?
Yes, sir.
Okay.
Yes, sir.
I am giving you a problem. Okay. And before to that, just let me open. Let me verify our theoretical concept, which we have discussed in theory. You have to design this thing now. What is my screen visible to everyone? Is my screen visible?
Yes, sir.
Okay. A loop antenna you design with some dimension, whatever we have designed just now. Okay. With the similar dimension, okay, make a square loop antenna also. It means I want a loop antenna which is designed like this. Two ports are there, and these are the two concentric wire line. You have your experiment will be, you can note down. Experiment 6, sorry, experiment 5. Design of a planar loop antenna in circular loop and square loop. Circular loop and square loop. Didi, I'll call you in 5-10 minutes. 5-10 minutes, huh? Okay. Yeah. So a circular loop antenna. Here you can see that if you make a circular loop antenna, the area of the loop should be equal to this. Can you design with this? Here you have to use bricks to connect, isn't it? Can you model it? Say yes or no.
Yes, sir.
So here area of square, whatever is coming, area pi a square for this. For example, currently what we have taken, an internal radius was 13. So pi a square was our area. Take this area, how much it is coming, into that, take same area, and that will be d square. It means that will be the length of this. So on the same orientation, design a loop antenna in square also. Is it okay? Is that okay? You don't want any information from me. Same wire thickness should be there. I don't think so any problem is there. Everyone is able to understand this. Venkatesh, Mahendra, Gatram,
Yes, sir.
Jasi. Could you understand what we are going to do now? Here you have designed a circular loop, right? Now in the
Yes, sir.
same orientation, it means with the same dimension, 13 is the inner radius. So first loop is 13. So actually you can do similar thing for that also. Same, take a brick, and from that brick make a structure. What will be the d dimension? Okay, connect them together. Let me just show you a glimpse of this, how I'm going to do. First of all, calculate it properly, that how much is the area coming. Here 5 pi a square, which is coming for the inner loop in the same dimension. You have to select here in the modeling. select the brick, and the brick thickness should be equal to that wire. Okay, because we are not, or you can do one thing, you can use a circular wire. Yes, a circular wire you can use of the same dimension, and you are going to decide it in this way. First in this orientation, how much is the wire? D. This orientation D, this orientation D, this orientation D. Then circle point here to here loft with a 90-degree angle. Circuit point like we did in the folded dipole last time, isn't it? Isn't it? We can do
Yes,
it
sir.
or not? Yes. Try this, please, everyone, and then connect it like this. But keep in mind the area total which coming, like this is D, this is D. So D square should be equal to, because it's a square, so square have the area equal to loop. Then we can say both the loops. What is this area here? Pi a square. This pi square a square divided by a distance, divided by pi a square is the area, no? So area is equal to D square, total is coming, that area should be equal to D will be root of this. So take the root of this simply. Okay. Whatever is the circle area is coming, take the root of this. So it means pi into 13 is your current area. Inner radius we have taken. You can take outer also. So we can say pi into 15 square, root of this is going to be your D. Isn't it? Because for a circle, area is equal to D square. Arm, right? Both the arm will be square. So D will be this much. Take the D, make the 4 cylinders first here. No brick, please. Take this cylinder, make this dimension, this dimension, this dimension, this dimension. Join them, connect the faces like this, or you can take, you can use the mirror or copy whatever function, but you should be aware in which direction what you are creating. Is that okay? Then again insert from center to here same brick, cut it, so you will have a loop output here. Then after this remaining section which is there, copy it, and no, then you have to create it for outside one more loop, that will be complete. Then outside one more loop, that will be complete. For a square loop, solve the problem, check the radiation pattern. I want a proper comparison of a circular loop and a square loop. Is that the problem clear to everyone? For the same frequency what I have given today. Same frequency 0 to 6 gigahertz. Observe the radiation. Clear everyone?
Yes, sir.
Okay. Best wishes for this. Let me take attendance for the 2 hours now. And next class, I'm going to check this because today we have done a wonderful job. We have completed our last practical remaining part also, folded dipole, and also a new antenna we learned today, that is designing of a folded loop antenna, sorry. So with this, any question, please? Any question? You can ask it here. If any question is there, you can ask it here. If no, let me go for attendance. Can I take attendance now? Can I take attendance?
Yes, sir.
Attendance, please. 007, sorry, 301.
Present, sir. 301.
Okay. Continue, please. 27.
27 present, sir.
Okay.
36, yes, sir.
Okay.
40, yes, sir.
Okay.
42, yes, sir.
Okay. 49. 49, are you there? Absent. 57.
57 present, sir.
59 present, sir.
Okay.
68%, sir.
Okay.
85 present, sir.
Okay. You already said 45. 85. 89 absent, no? Jason Jeffrey. Inform her or him. Who is she? Is a girl or boy?
Boy, sir.
Yeah, inform him. He's missing several classes. I'm going to inform this to his FA. Okay, 94. 94. Absent. 101. Absent. 103.
103 present, sir.
Okay. 112.
112 present, sir.
121.
121 present, sir.
128.
128 present, sir.
133.
133 present, sir.
Okay. 150.
150 present, sir.
182. 197.
182 present, sir.
197 present, sir.
Continue, please. 201.
201 present, sir.
Yeah.